Welcome everyone to Bridging the Gap, AI Strategy and Tech Insights. Today, we're diving deep into a fascinating challenge in the world of large language models, how they learn and, crucially, how they generalize that learning. We have a fantastic panel of experts ready to unpack a recent study that sheds new light on this.
Great to be here. This is a topic that keeps business leaders up at night. We invest heavily in customizing these powerful AI models, but sometimes, well, the results aren't quite what we expect.
Exactly, we primarily adapt these large pre-trained models in two ways: in context learning, or ICL, and fine-tuning, or FT. Think of ICL like showing the model a cheat sheet right before the test. It sees examples in the prompt itself. Fine-tuning is more like sending it to school, updating its core knowledge through training on new data.
And that's where things get tricky. Fine-tuning, despite being a deeper schooling, can lead to surprisingly brittle knowledge. The classic example is the reversal curse. You fine-tune a model on Daphne Barrington directed A Journey Through Time, but it then fails to answer who directed A Journey Through Time, given Daphne's name as an option.
So it learns the fact in one direction but completely misses the reverse. That seems fundamentally limiting for practical use.
It is, and it highlights a difference in what the model actually learns. To really isolate this, the researchers behind the study were discussing constructed some clever synthetic datasets. They used nonsense words like femp and glon for entities and properties.
Why the nonsense words? Sounds like trying to teach advanced calculus using made-up numbers.
Ha, not quite. It's more like creating a sterile environment for a sensitive experiment. Using nonsense words ensures the model is learning only from the data provided during fine-tuning or in context, not drawing on potentially related knowledge already baked in from its massive pre-training on the internet. It gives us a clean test of generalization.
That makes sense from a research perspective. For businesses, though, the practical outcome is key. The study found that often ICL, just showing the model the training data in its context window, led to better generalization on these tricky tasks like reversals or simple logical deductions, syllogisms, compared to fine-tuning on the exact same data.
It's quite the finding. ICL, the cheat sheet method, sometimes outperforms the deep schooling of fine-tuning when it comes to applying the knowledge flexibly, at least in these controlled setups. It suggests the underlying mechanisms, or let's say, the inductive biases of these two learning modes are quite different.
So strategically, does this mean we should abandon fine-tuning for certain tasks? If ICL is more flexible, maybe we just need bigger context windows and feed the model everything it needs on the fly. It sounds potentially simpler, maybe even cheaper up front.
That's a great strategic point, expert one. But hold on, the cost and latency of running massive contexts for ICL consistently can be really prohibitive, especially at scale. Imagine stuffing an entire employee handbook into the prompt every time you ask a simple HR question. Plus, you might hit context length limits. Fixing fine-tuning's generalization is still critical for robust, efficient deployment.
And that's exactly what the researchers aimed for next. They asked, can we take the strengths of ICL, its ability to make flexible inferences on the fly, and use them to improve fine-tuning?
Okay, how do you get the best of both worlds? Sounds like wanting your cake and eating it too.
Pretty much. The core idea is called dataset augmentation. You essentially use a powerful model in ICL mode to reason about the original fine-tuning data. You prompt it to generate variations, rephrasings, reversals, even simple logical inferences that follow from the training facts.
Think of it like this: if the training data says femp are more dangerous than glon, the augmentation process might generate glon are less dangerous than femp. Or if the data has all glon or yomp and all trough or glon, it might generate the syllogistic inference all trough or yomp.
So you're essentially pre-digesting the knowledge, making the implicit relationships explicit before fine-tuning begins. It's like providing worked examples alongside the textbook problems.
Precisely. You then add all these generated augmentations back into the fine-tuning dataset. The study showed this significantly improves the model's generalization from fine-tuning, often bridging the gap to, or even exceeding, the performance of ICL on the original data.
So, we're basically asking the AI to generate better study notes for itself before the final fine-tuning exam. Sounds like something my college roommate definitely tried, probably less successfully.
Chuckles, let's hope the AI is a better student. Another technique they mention that helps, especially with these augmentations, is sentence splitting. If your training documents have multiple facts, breaking them into separate training examples seems to help the model learn each piece more effectively, possibly avoiding interference between facts within the same example.
But here's a nuance the study also uncovered, particularly with their semantic structure benchmark. This was a more complex dataset with a hierarchy of concepts, like a mini Wikipedia of nonsense animals and objects. On this richer dataset, standard fine-tuning did show some ability to generalize to reversals, even without augmentation.
Wait, so the reversal curse isn't always a curse.
It seems less potent when the facts are embedded in a larger, coherent knowledge structure. Perhaps the model can use related facts as alternative pathways to infer the reversal. If it knows Grud's dogs are Abmez mammals, and also learns Gruds have fur and Abmez have fur, maybe that helps reinforce the connection and support the reversal. Abmez include Gruds. It's not just learning isolated A-B pairs.
Hold on a second, everyone. We're all getting excited about making fine-tuning more flexible, essentially making it better at mimicking ICL's generalization patterns. But are we absolutely sure that maximum flexibility is always the right goal for fine-tuning?
Ooh, a challenger appears. Go on, Expert 7.
Well, one of the potential advantages of fine-tuning is its stability and predictability. You train it, you test it, you deploy it, and you have a certain confidence in its behavior on tasks similar to its training. ICL, especially with very long contexts, can sometimes be surprising. Are we potentially sacrificing some of that predictability in the chase for pure flexibility? Maybe the goal shouldn't just be flexibility, but controlled, reliable flexibility.
That's a provocative thought, Expert 7. I'd argue, though, that the augmentation method described isn't just about mimicking ICL blindly. It's about making the fine-tuned model more robust by exposing it to the logical implications of its training data. The paper shows it improves generalization on specific, challenging metrics like reversals and syllogisms.
Perhaps deepening understanding, yes, but the process involves generating synthetic data using the model itself. We need to be cautious about whether this introduces its own subtle biases or failure modes that are hard to predict. It warrants careful consideration alongside the performance gains.
This is critical from a business perspective. We need reliable AI. If this augmentation technique makes fine-tuned models significantly better at understanding nuances, handling variations in user queries, and correctly applying learned knowledge, that directly translates to better products, fewer errors, and potentially faster deployment cycles for customized AI solutions. That's a tangible ROI.
It also changes the calculus for development. Instead of just throwing more raw data at a fine-tuning problem, this suggests investing compute during the training preparation phase. Using the model to think about the data can be more effective. It reminds me of the 80-20 rule. Maybe 20% of the effort spent cleverly augmenting the data yields 80% of the generalization improvement.
Absolutely. This ties into a concept from cognitive science Tania Lombroso calls learning by thinking. The idea is that computation itself, without new external input, can make existing information more accessible and usable. The model isn't learning fundamentally new information from the ether during augmentation. It's processing its existing data to surface the latent logical connections.
I like that adaptation. So we're moving from just data quantity to data quality and structure, enhanced by the model's own reasoning power.
And this augmentation doesn't have to be perfect. The study used model-generated inferences, which aren't guaranteed to be flawless, yet they still significantly boosted performance. It suggests the process is somewhat robust.
It also highlights the idea of train-time inference scaling. We often talk about scaling compute at test time, like using chain-of-thought prompting or scaling during pre-training, bigger models, more data. This work shows scaling compute during the fine-tuning process itself, specifically for intelligent data preparation, is another powerful lever.
So for my peers in leadership, When your tech teams talk about needing more time or resources for data augmentation during model customization, this research suggests it's not just busy work. It could be the key to unlocking the reliable, flexible intelligence we actually need from these systems. It might mean shifting budget from just more data collection to smarter data preparation.
We should also consider the life cycle. Fine-tuning augmented data might create a more robust baseline, but knowledge still gets stale. How does this interact with continuous learning or model updating strategies? Does augmentation need to be part of every update cycle?
And the validation challenge remains. If we use AI to generate training data, how do we rigorously validate that synthetic data, especially the inferred parts, to ensure we aren't inadvertently reinforcing biases or introducing subtle errors that only show up later in edge cases? That's a crucial governance question.
The paper also briefly touched on process knowledge, learning procedures rather than facts. They used a synthetic task like learning weird new rules for derivatives. Preliminary results, there also hinted that ICL was more data efficient initially, but augmentation could help fine-tuning catch up. It suggests these principles might apply beyond just factual knowledge.
Fascinating. It really feels like we're moving beyond simply training models and starting to understand the different ways they learn and how to guide that process more effectively. We've covered a lot: the surprising limits of standard fine-tuning, the flexibility of in-context learning, and this powerful idea of using AI's own reasoning to create better training data for itself.
The key takeaway for me is that optimizing LLM performance isn't just about scale anymore. It's increasingly about smart, targeted techniques like this augmentation method to achieve reliable generalization.
And the research highlights that the dichotomy between ICL and fine-tuning isn't fixed. We can blend their strengths.
With the important caveat that we need to remain vigilant about the implications and validation of these powerful new methods.
Absolutely. Well, that's all the time we have for today. A huge thank you to our experts for shedding light on this complex but crucial area. It's clear that understanding how these models learn is just as important as what they learn. Join us next time on Bridging the Gap. This study explores how large language models generalize novel information. It compares two learning methods: in-context learning and fine-tuning. In-context learning provides examples directly within the model's input prompt. Fine-tuning updates the model's internal parameters based on training examples. Researchers created new datasets with fictional facts using nonsense words. This isolated the tested knowledge from the model's prior pre-training data. These datasets tested generalization on tasks like logical reversals and deductions. A reversal involves inferring B is A after learning A is B. A deduction involves combining multiple learned facts to reach a new conclusion. The study found in-context learning often generalizes better on these specific tasks. Models frequently failed to learn reversals through fine-tuning alone. This confirms a previously observed issue called the reversal curse. Fine-tuning also showed limited ability to make complex logical deductions. In contrast, in-context learning handled these challenges more flexibly. The researchers proposed improving fine-tuning through dataset augmentation. Dataset augmentation adds model-generated inferences to the fine-tuning data. The model first creates inferences like reversals or deductions using in-context learning. These generated inferences are then added to the data used for fine-tuning. This augmented fine-tuning significantly improved the model's generalization ability. Performance with augmented fine-tuning often matched or surpassed in-context learning. The results indicate distinct learning tendencies between the two methods. Fine-tuning showed some generalization improvement when facts were part of a larger structure. However, in-context learning and augmented fine-tuning remained superior overall. A limitation is the use of nonsense words, which might affect model performance. Results primarily used one model family, requiring further validation on others. The work suggests model generalization can be improved using computation during training. Adding model-generated inferences makes learned knowledge more accessible and flexible.